Half-life is simply defined as the time it takes for a sample to be cut in half. And that can apply to chemical reactions or nuclear reactions. So for example, we use that concept in carbon dating, where carbon-14 decomposes slowly via a nuclear reaction called beta decay, and so the T1 half is equal to 5,750 years. And so this would be a first order type dependence because it is independent of the initial concentration. No matter what your concentration, high or low, it's always going to take this particular time. Now you're going to be provided with for these kinetic reactions with all the formulas that correspond to the order. And so if you look here, it simply depends. The time T1 half here, the time it takes to cut the sample in half, is simply dependent on K only, so it's a constant. Of course, it differs from different reactions, right? If it's in fact, nuclear decay has different kinds of half-lives, and uranium is even longer. It's in the billions of years. So that's why the nuclear waste from chemical power plants is such an issue, because it has such a long half-life. So this here shows you nicely how your sample for a first order reaction gets cut in half, and then your rate levels out, right? So your rate really never, or your concentration never really appears. It's just your rate of decay slows. But you can take any of those samples and say if you have 100% to begin with, you just simply cut that in half. So over a 5,750 year period, you end up with 50%, and then another 5,750 years, you end up with 25%. You just cut your sample in half, and you're gonna. Another thing to add is, of course, for 0 and for second order half-life, you also your time also depends on the initial concentration. So I may ask you to calculate the initial concentration or the time. You should be able to use algebra to do either one of those calculations. So let's take a look here. So example from the book, we have a decomposition, arbitrary. A compound AB decomposes to form elements A and B, or compounds A and B. It's irrelevant. It's a chemical reaction. We do not know what order it is, but I give you a hint. I say a plot of 1 over A versus time yields a straight line with a slope of 0.055 per molal per second. Now there's two hints here. One are the units of K, and then this plot. And you don't have to remember that this is second order, but this is second order. A plot time versus 1 over A that's linear is always second order, and a K, that is because the slope then would be equal to K in this case would have a per molal per second. And where do I get this information from? From this chart, which obviously I'm going to provide to you. You look simply, where's the plot 1 over A here? There it is, versus time straight, meaning second order, and here are also the units of K. And the bottom line here is we have a second order reaction. We can determine K from the slope, and the slope is basically equal to K, and so I can say what is the value of the rate constant K for this reaction at this temperature. Well, it's simply equal to K. I mean the slope, so K is equal to 0.055 per molal per second. Write the rate law of this reaction. So we have the rate that's going to be equal to that K, and since I know what it is, I can write 0.055 per molal per second, and then it is the concentration of AB. Always use the brackets, that's molarity, and because it's second order, I have to put that superscript 2. Alright, so we have got A and B, but there's C and D. Now for C, I want to know what is the half-life when the initial concentration is 0.55 m. We go to the chart. I won't go there now. I'll just simply tell you that T1 half is equal to 1 over K times the initial concentration of A, right? And so I can just plug that in. So it's going to be 1 over, we know what K is, 0.055 per mole per second, and then we multiply by the initial concentration provided here times 0.55 m. And so moles per mole divided by mole, and then 1 divided by 1 divided by second equals seconds. So this is going to be a time as we expect, and if you put this in the calculator you get 33 seconds. And now I'm asking you if the initial concentration of AB is 0.25 molar. The reaction mixture initially contains no products. What are the concentrations of A and B after 57 seconds? So this is not a half-life question. This is a integrated rate law a question, and so the only thing you need to pay attention to is that it's asking not for the concentration of AB. The equation we will be using, the integrated rate law for second order, is for the concentration of AB, but you also are told that you have 0 products. Okay, so the reaction mixture initially contains no products. That means that so this is 100% at the beginning, and then whatever that depletes, right? So if this proceeds 50%, then we have 50 and 50 here, right, or 50 moles. And so if this is if 60 of it disappeared, then we have 40 over here. So the integrated rate law from the chart is that the concentration of AB at time t, which is 75 seconds in our case, is equal to 1 divided by the time, which is 75 seconds, times the concentration, times K. Maybe I'll go there real quick after I'm done just to show you. 55 per mole per second times 1 divided by the initial concentration, which we are told is 0.250 m. And if you crank that out, again, this cancels here. This also cancels, and so we end up with a concentration of 0.123 m, but that is the concentration of AB, and we want to know the concentration of A and B, so we have to subtract 0.25 m minus 0.123 m, which is equal to 0.13 m, and that is the concentration of A and B because they are in a 1-to-1 ratio. So for every 1 mole decomposed of AB, we get 1 mole of A and 1 mole of B. Let me go back real quick just to show you. So the integrated rate law is this equation here, and that's what I was using. This is T at 75 seconds. This was the concentration, 0.25. Okay, moving on to a different topic. Alright, so this is called an energy profile or reaction progress, or sometimes you see this as a reaction coordinate. Alright, it's simply a graph of energy of the reactants and the products with respect to each other. And so the reaction is shown here. It's just hydrogen and oxygen gas. We know that hydrogen and oxygen gas, they don't react with each other unless we stick some energy in. So in order for this reaction to occur, you actually have to put in some energy. You have to ignite it, or sort of raise the energy, the kinetic energy of these products. So, but what's the reactant? So, but what's shown here is the energy of the reactants. So hydrogen and oxygen shown here. Here's oxygen, 2 hydrogens, and so you have to break those bonds. So you stick energy in, and then you release energy when you reform the bonds. And so here are your products. And so there's a thermodynamic aspect to these graphs and a kinetic aspect, right? So our thermodynamic aspect is that the difference here between the energy of the reactants and the products is negative. So that means energy was released the products have lower energy, and actually lower energy but stronger bonds, right? Because you have to stick a heck of a lot more energy in to go back here, right? So but this energy from the reactants to products, which is negative, so this would be representative of delta H of this process, and it is negative, which means it is exothermic, so it's thermodynamically favorable. So this is a thermodynamically favorable reaction, and the reason it doesn't proceed instantaneously is because of the kinetic factor, right? So the energy of activation is rather high, right? And so sometimes reactions can have low energy barriers, and then sometimes if we want to speed up a reaction, we can use a catalyst which actually lowers the energy of activation to proceed to force a reaction to proceed further. So how do we get over this energy barrier? Well, basically thermal energy will do this trick. It doesn't always work, right? If a chemical reaction takes place in our body, we don't want to heat our body up to 200 or 300 or 400 degrees Fahrenheit, but in this particular case we can. So if you look at a graph of the kinetic energy here at a particular temperature, let's say T1 here, right? You have a distribution. The molecules, some of them are moving faster, some of them are slower, but the mean is right here at this maximum. And so some of these molecules that are moving faster, they are in this area, they can actually react, and so some of them will. But it's just going to be a slow reaction, which is a kinetic aspect, right? So it's thermodynamically favorable, which means the reaction will proceed sooner or later. But in order to push this over, if we heat it up, see how when we heat up, increase the temperature, we increase the kinetic energy, those things move faster, they bounce into each other, and when two of these hydrogen and oxygen atoms bounce into each other, they have sufficient energy, they can break and react and form. And so if you push this all the way to this activation energy, the reaction will proceed. Okay, and then energy is released. So that's how you accomplish that for the most part. You increase temperature. Increasing temperature will speed up a reaction or get it to go over the energy barrier, especially those that are kinetically unfavorable, which means, or non-spontaneous, which means they have a rather large activation energy. Okay, so there's something called the Arrhenius equation, and the Arrhenius equation relates the temperature and the equilibrium constant to its activation energy. So the rest of these values here, most of those are constant here, right? The temperature is a variable, and then you can solve for the energy of activation, where A is a constant referred to as the frequency factor, and E is just Euler's constant, so it's an exponential relationship. T is the temperature, which has to be measured in Kelvin, and then R is actually the ideal gas constant, because it's about elements or atoms, reactants that are in the gas phase. And so the units that we're using are joules per Kelvin per mole, and so you'll be provided, if I have you use this equation, you'll be provided with it, with all of those, the equation itself, the constant, and the frequency factor and everything, and then so and K. So what you can do is, if you are given this equation, you can solve for that. The activation energy of a reaction is 56.8 kilojoules. Here I'm having you solve for the rate constant, so it's just simply plugging in. So K is going to be equal to A, the frequency factor. It's told to be 1.5 times 10 to the 11 per second. Now we do the Euler's constant, which is 2.8 something, to the negative EA, energy of activation, which here is given in kilojoules, but our ideal gas constant is in joules, so we need to convert that. So it is 56,000 800 joules per mole, that's the activation energy, divided by R, 8.314 joules per K and per mole. And what we're missing is the temperature, and we're told it's in 25 degrees Celsius. Here you go. We have to convert that to Kelvin, so it's 273 plus 25 degrees Celsius, which is 298 degrees K. That goes in here, 298. Get a calculator, crank this thing out, and my calculator says 17 per second. So K is equal to 17 per second. So that's not that hard. You just plug it in. Got to pay attention to the units, make sure everything is converted properly. You can't plug in kilojoules, and you sure can't plug in Celsius into this particular equation. Here it is, neatly solved. You know, you already know that we like to put things into a linear form. And what do you know? We take this Arrhenius equation and we arrange it so that it represents a linear equation. And when we can do that, we can take some real data, use Excel and plot it. And so what you plot is natural log. What you do is you graph the natural log of K versus 1 over T. So K changes with temperature, and that's why those are two variables, so you can collect. In fact, we are doing this in the lab. We're going to actually collect kinetic data for a particular reaction at different temperatures, determine the K, and we will plot this, and we will then solve for EA graphically, because the slope then is equal to minus, it's written here somewhere, the slope is going to be equal to negative EA over R. And so we can then simply solve for EA, or the energy of activation, by using Excel, right? So I'm not going to show you how to do this in Excel again. You've seen this like 3 times already. But what you would want to do is you would want to plot the natural log of K versus 1 over T. So you have to, in Excel, tell this to do 1 over T. And so you're given K, and so then you do the natural log of K, and you plot that. And when you plot that, and here's the result, the slope is going to be equal to negative EA over R, and then you simply just solve for the energy of activation. In this case, it turns out to be 93.1 kilojoules per mole. Of course, if you have real-life data, the better your data is, the more data points you have. Here you have 1, 2, 3, 4, 5, 6, 7, I don't know, 12 or so different points. The more data points you have, the better your data. But in order to create or make a line, you just need 2 points. All right, so 1, 2, and you can make a line. And if your data is good, you can actually get pretty close to that energy of activation. So there's an Arrhenius equation that's called the 2-point equation, and that you can actually do on an exam, because you don't need to plot that in Excel or manually. You can just use the equation. And so the 2-point equation has K1 over K2 and T1. So what you need is, you need this equation, which I will give you, and you need 2 data points, right? So you need the equilibrium constant at a temperature A, and you need the equilibrium constant at a temperature B. And so as long as I provide you with that, then you can solve algebraically for the energy of activation. So the example given here is, consider the reaction between nitrogen dioxide and carbon monoxide. Reaction provided. The rate constant at 701 K is this, and the rate constant at a higher temperature is higher. Okay, so that is right there, should tell you we are going to use the 2-point equation. We have 2 data sets. Find the activation energy. So 2-point equation, and I'm not going to work through it. I'm just going to show you, right? You just plug it in, T1, 1 over T1 minus T2, so 701, and 895 go here, and then R is the ideal gas constant, which will be provided to you. It's not written here, but it's here. Yeah, here this R, 8.314 joules per mole per K. And when you solve for the energy of activation of this process, and you know, the energy of activation doesn't change with temperature, right? So just to highlight that, right? Because we earlier looked at a graph at the reaction diagram, and so we had oxygen, we had the reactants here, and so this energy of activation it is always the same. So this, in this particular case, is 145 kilojoules. So whether you get over that hump at 700 degrees or at 895, that doesn't change. The only time that changes is if you use a catalyst. Alright, so I'm going to stop here and come back and start with catalysts and mechanisms, and that will be our last lecture.